In previous training, we have seen how the oil passing through the bearing system is critical to the correct operation of the turbo. The sealing system is designed to keep the oil where it should be, inside the center housing, but it is the most misunderstood feature of a turbocharger. Many instances of oil leakage are wrongly blamed on a perfectly functioning turbo. Understanding how the sealing system works helps greatly in diagnosing possible root causes on the vehicle and will minimize wasted workshop time. Vehicles and engines use a variety of oil seals. The most common of these is the lip-type contact seal, which are highly effective, working with rotating shafts like the crankshaft. If one of these starts to leak, it is relatively easy to diagnose and rectify the problem by replacing the seal. A turbo does not use this type of seal due to the high speed, extremely high temperatures, and the large shaft clearances necessary for correct operation. If oil is found to be leaking from a turbo, firstly, it is more complex to diagnose correctly, and secondly, there is no possibility to just change a seal like on a crankshaft. Changing the turbo may not cure the problem, as the oil leak is very often just a symptom of some other problem on the vehicle. Turbochargers use a dynamic differential pressure sealing system. Dynamic because it utilizes the rotation of the shaft, and differential pressure because it takes advantage of the normal pressure differences between the three housings of the turbo. Under most running conditions, the pressure in the turbine housing is higher than the center housing, and the pressure in the compressor housing is higher than the center housing. At the turbine end, the sealing system is simple. After the oil has finished its work in the bearings, it travels along the shaft until it reaches the hub, where the spinning oil thrower literally throws the oil outwards by centrifugal force, and it meets the inside face of the center housing, where it drops down under gravity to be collected by the oil drain and returned to the engine sump. In addition to that, 1 or 2 piston rings are used, which fit into a very accurately machined stepped bore. Unlike the piston rings inside the engine cylinders, these piston rings do not move. During the assembly process, the piston rings are compressed, and once they are correctly located, the piston ring never changes position. A natural feature of any piston ring is that it can never be a 100% seal, because there must be a running clearance at the two ends, plus clearances all around the rectangular section of the ring. However, in the turbo, this natural feature is used to advantage, as some of the high-pressure exhaust gas from the turbine inlet passes behind the turbine wheelhead to provide a very effective pressurized seal around the piston ring to prevent any oil from passing out of the center housing. The tightly controlled piston ring clearances allow a very small flow of exhaust gas to pass from the turbine housing into the center housing, further helping to keep the oil where it should be. On some turbos, we may use bleed holes in the heat shroud to further increase the pressure in the piston ring area. At the compressor end, the sealing system is more complex, and there are many different designs to work with specific turbo models and applications. As the oil finishes its work in the journal bearing, it spills out and is thrown outwards under centrifugal force by the back face of the thrust collar, whilst the oil from the thrust bearing is also thrown outwards by the rotating thrust collar, where it again drops down under gravity to be collected by the oil drain. The thrust collar may be a simple disc, or it may be a combined thrust collar, incorporating an oil and air separator, and thrust spacer, incorporating 1, 2, or even 3 piston rings, depending on the application for the turbo. To understand how the seal works, We need to see the compressor working in two different conditions. Firstly, at high speed, there is a large flow of air through the compressor, and some of the high-pressure air from the diffuser section bleeds behind the wheel and pressurizes the piston ring seal. A small flow of air helps to keep the oil where it should be. Secondly, at low speed, the flow of air through the compressor is much lower, so the pressure at the diffuser section is much lower. And under these running conditions, the pressure behind the compressor wheel can be negative, allowing a small flow of air to be drawn from the center housing past the piston ring and into the compressor. Under these conditions, it is essential that the oil and air in the center housing are separated to prevent any oil from also being drawn into the compressor housing. Any oil splashing around internally may pass around the rotating thrust collar and down towards the piston ring area. As oil travels towards the inner part of the thrust collar, it passes a row of radial holes. The heavier oil is thrown outwards under centrifugal force and into the oil gallery. The holes are a two-way passage, so as oil is thrown outwards, air is drawn down through the same radial holes, and then along past the piston ring into the compressor housing. So the oil and air have been separated to prevent leakage into the compressor. Another way to separate the oil and air, which is used very effectively on many modern turbos, is to use an oil deflector, which collects oil passing out from the thrust bearing, reducing the amount of oil which can reach the oil thrower. A knife edge type of oil thrower is used and very effectively helps prevent any residual oil from splashing into the piston ring area. On dual sequential turbos, where only one turbo runs full-time and the secondary turbo only operates on demand, it is necessary to provide effective oil sealing even when the turbo is not rotating. This is achieved by pressurizing the piston ring seals using air provided by the primary turbo. An air pipe connects to the center housing, and the high-pressure air travels through internal feed channels, providing a flow of air between the piston rings. This helps to prevent oil leakage from the center housing, even when the turbo is not rotating. The center housing to backplate joint includes a square section O-ring, which is compressed as the backplate bolts are tightened during assembly. One part of the sealing system that is often overlooked is the sealing of the backplate retaining bolts. On many turbo models, the backplate bolts pass through the oil gallery and into threaded holes in the center housing. This means that the bolts often have additional seals to prevent the hot, thin oil from traveling up the thread, passing under the bolt head and into the compressor housing. We may use bolts with an annular V-shaped ridge, which bites into the backplate surface to create a permanent seal, or bolts that have washers with a rubber seal, which is compressed under the bolt head and prevents oil from leaking into the compressor. So, the sealing systems on turbos have evolved over many years and will continue to do so as engines and their associated systems become more complex. The sealing system has been proven to be exceptionally efficient and robust, so leakage from either the turbine or compressor end seal is almost always due to some external influence. Our next animation will show what may cause a perfectly functioning turbocharger to suffer from oil leakage.